other than that, then we got the graduate meeting on Thursday.
Yes. I guess we could still go look at the venue before the meeting.
Yeah, he emailed me back and he said we can go whenever.
Okay.
So.
Oh my God, Jacob.
You couldn't find.
I just saw you.
Oh, did you shave?
Yeah.
Nice. Me too. Can you tell?
Yeah.
No, you can't tell. I didn't have a beard like you, Jacob.
I felt like a wildling.
Yeah.
I look like I got lost in the cave and, they found me.
Oh, am I transferring of answers? Oh, it's so annoying. Am I transferring of answers over for my scratch work, for my final work? I forgot to transfer over 4C. I did it and I just forgot to transfer it over, so I went 4A, 4B, 4D, and just kept moving. So I just shot my own grading.
I want to say transferring because I transferred them and I just messed up the transfer thing.
This month is already been crazy.
I've had this weird like cool down period between two periods of death. Where,
You mean break, right?
There's this brief moment after midterms where you think you can breathe, and then you take a breath, and then it just all comes right back.
You take a breath and you're like, why did I do that? I should have
Yeah.
never stopped to
Yeah.
breathe.
Yeah. Yeah.
don't say that.
Don't let it lure you in.
No.
It's waiting right around the corner for you.
Don't be food. Did you look at StatMech homework?
I'm still trying to finish previous StatMech homework.
You got this. I just did about like 50% effort on that last one. It turned it in so that way I could have one less thing on my plate. So
Every time he gives us one, I look at it, and I'm like,
It's kind of.
I don't know what you're doing.
yeah,
Like,
it would be helpful if you had solutions. Do you think?
yeah, or if he graded them.
Fair.
Finish your meeting. Okay,
Yes.
we'll come back from the break and you will actually, it's time already, right? You did good job. I think you all gave a good answer. That is what I expected after you have a two hard homework, I think, and then you do this effort. Then just a few small mistakes for each. If you have any question, let me know. And others, everything's okay. Now let's continue. We will finish the topics on chapter 3 today. The last topic about the time evolution of the quantum states, right? We already discussed for the time evolution of quantum states follow the Schrodinger equation. And that is Schrodinger equation, the postulated type. And in this, we discussed this one, IH bar partial T actually is equal to H. What that means? This operator controls the change of states as function time, right? So that is very important, and later today we are going to also discuss why the Hamiltonian is control change. It is associated with this unitary transformation with the time translation. So that is the first issue, and the second one, we introduce time revolution operator, U, T, T naught, that turn from states from T naught to T. And we already derive or get this expression of this type of change. Is minus. Yes. Okay. And so we know this is a unitary operator. We already discussed properties. Then we come to the third one. When the Hamiltonian does not depend on time explicitly, we know the state can be separate. Okay, I'm going to discuss this one, your question, and try to answer today again. So the state can be separated into space part and time part. Then when we substitute into the Schrodinger equation, we found the Schrodinger equation decoupled into two parts. First equation only for time-dependent function, and that we get the expression or solution is an exponential function. E is this constant energy of system, right? And time. The second part is the partial part is resolved. We call the time-independent Schrodinger equation. Hamiltonian apply this to give us energy, and this is the solution. This is nothing but this eigenvalue problem in chapter 2. We will get the eigenvalues for Hamiltonian, and we get eigenvectors, right? So that is the details how to solve this. Of course, from chapter 4, we are going to discuss detailed system. Then, if for the stationary states or not any states at any time, we can get in terms of the eigenstates of Hamiltonian, eigenvalue of Hamiltonian, and this coefficient is the project of this is the initial states, T naught project to the eigenstates. So what that means, once we know initial states, we can calculate the coefficient, right? The initial states may be the combination of all states or just one of the eigenstates, whatever. Then you have the coefficient. So any after that, from T naught to any time, the wave function is follow this, right? And then we discuss the total probability. We know total probability is always 1. That means finding the particle in somewhere in the whole space is always possible, right? Because the charge or matter or system conservation, we cannot destroy it or create it suddenly in some position. So that means the total probability is equal to 0, a constant time conserved, right? Does not depend on time. Today we are going to discuss in the details the probability density. This is total probability, right? Now how about the probability density? Then we are going to discuss how about this time evolution of expectation value. Since expectation value is what we observable variables, right? Then we discuss the symmetry with the conservation law, so that we will finish the chapter 3. Okay, let's first discuss the definition. So I'm going to use law, which is a function r and time that define. Okay. Let me do this way. That is in position representation. So that is equivalent R P is bra project to the position representation, right? And the cat project to the representation, the position representation, so that is nothing but the psi star RT product is this one. So this is not, this is integral, with integral from the whole space. This one, just at any position R and time, this product, we call this probability density. So now we are going to see how about this. Does it depend on time? And the answer is yes, but now we want to know how it depends on time. What kind of regulation or rule, right? So in order to study that, we are going to apply this to the Schrodinger equation. Since here, so now let's see, because partial rho, partial t is this product, right? So the first, do the partial derivative of psi star with time. and keep this sign here, then plus, second one is keep the psi star. This space here, that's not plus. Partial psi, t, partial t, right? Two terms. The next step. So now we are going to find what is partial psi star, partial t, and what is partial psi, partial t. They follow the Schrodinger equation here, right? So we are going to use, this is the first because this, and according to the Schrodinger equation, right? The partial, let's do this first, is 1 over I h bar Hamiltonian, right? By the Schrodinger equation here. It just divide h bar both sides. Then we take the complex conjugate, so this one takes its conjugate. Left hand side is this term, and right hand side we have this one, so you have minus, right? I complex conjugate is minus, right? If you take this denominator, but fine, you multiply I and I both sides, so this is I over h bar minus, right? Then I over h bar minus, so I became minus I, minus, and I became plus. So here, if you multiply I, you will have a minus, like this, right? Okay. And Hamiltonian, we know Hamiltonian Hermitian, right? Oh, sorry, I forgot. I want to explain this one again. Okay. So if we have the product of two cat, that means if in a different space. So this is in the spatial space. This is in the time space, right? So if a different space, we can product with two cat. If the same space, yes, that is forbidden. That makes sense? For example, later we are going to discuss spin. And the rotation, angular momentum rotation is a rotation around space, right? And then we have also spin. So the total eigenstates or total wave function is the product of the characterized spatial in the spatial space and another in the spin space. They are in a different space. So let me give an example here. If you consider, let me see use this one. We have another. So that is actually let's just discuss not count change. So we just let's first consider the time. That's a spin. Usually we use chi. Is this product? So this is a spatial space. They are in a different space. Spin space. That is fine. Or if you use a colon, it depends on that spin, right? So that okay, we haven't done this past spin, so that I'm going to keep it. So you will see that if this is dimension 3, this is another dimension. So your colon is this dimension is correspond to this, and this dimension is correspond to this. That is one colon, still one vector. That makes sense? Not colon multiply colon. Okay. So I think that try to explain this one, why it's allowed to have the product of two cats. That is only for the two different space. If they exist in two different space, then yes, that case. That is just extension over like the 3 dimension. You can R is X components, Y component, Z component. So they are in the different space in the quality with 3.
Is that kind of like having the generalized coordinates in the mechanics?
Generalized
With
coordinates, yes,
the
kind of
matrix
like a
representation?
momentum and general coordinates and momentum in the Hamiltonian space. Yes, we have right 2n. Yes,
Yeah.
something the 2 dimension. Yeah, they are all independent. Yes.
So anytime we see two cats next to each other, the
Yeah, that's
action
in two different
is a concatenation.
Is what
Concatenation.
concatenation?
means that cat 1 has n columns, cat 2 has m columns, and the result will
There's
have
two
n
n.
plus m columns.
Yeah, it's 2 n columns.
Yeah.
Yeah, okay, yeah, something like this n and then another n. So the total vectors will be 2n. In space is 2n space. Okay. All right, so now let's keep continuing. Now we just substitute this 2 into here, right? Now let's keep. So here, the left hand side is still partial rho, partial t. And the right hand side, we are going to substitute this one first. So we have a minus 1 over h bar. Okay. Position is not. Oh, okay. In this position representation, we know the Hamiltonian, right? So now let's keep continuing with this one here. Hamiltonian is 1 over h bar. Hamiltonian inside minus h bar square, right? 2m. This one and plus potential. That is this one and 1 right here. This one is minus 1 over h bar. Okay, so now let me just fix this. So partial rho, partial t. If you either this one first, this one second, that's fine. So that first is this one. Is a minus 1 h bar. This minus h bar. Okay. Let me put it inside, right? So that's inside. 3. And these are multiplied outside. And then second term is this one, right? Is plus. And then this 1 over h bar inside minus 3. Okay. Okay, sine. Okay. So you can see first let's look at this first. This term. The potential it is operator, but it is function r, right? So we can, it will not like a momentum or Hamiltonian with like a partial or Laplacian. So you can change the position, or the position doesn't matter. That means here, this one, this one multiply this one is equal to this multiply this one, right? So the sign is just opposite, right? So they cancel. And the remaining part, okay, let me take this. I have the factor, this factor also take outside, right? Minus h bar square over 2m. So the inside is, this only do this gradient for this one, right? And multiply. And minus, since we have a negative sign, right? If I take this minus, so this is the one is here. Okay. Minus plus. So h bar square cancelled. Then I multiply I on the numerator, so I have another negative, right? IH to n, right? inside, let me write again, so now you know this one. We'll introduce another quantity we define. This is nothing but this we call the probability current density. Let's see. Okay, so I'm going to take this one as the inner product of grading with, okay, let me first write the result and give you. Okay, let me see somewhere the sign again. This is negative. So you see here, if I do this, I first do this one, right? Grading this one, keep this one, and then grading second one. And then this one to minus grading this one, so they cancel that. Only the second one is grading this one. So yeah, that is this one, that is this one. Yes, okay. So then, let me first write down the result and get introduced. That is we introduce G. So G is defined like this. G is I H bar for M and sine E H bar minus probability and current density. Because if you remember, you learned, I mean, this electromagnetic theory, right? E and M. And if you E and M, if this is a chart, okay, I think this is the formula. So that formula is like partial rho, partial P plus the divergence of this probability current density. And familiar this formula in the chart and curve, right? So that means what's the conservation here? That means how much charge flew, or if you consider a circle, it's a closed surface. You look the charge change as quantum time, the density, that means some of out of the surface will come in the first surface. You always keep conservation of a charge, right? So this is a conservation of this probability. In quantum mechanics, and that makes sense since we know the particle or the matter cannot discrete or critic, right? So that is
Dr.
this
Yu, I
one.
have a question.
Yes.
So would J be just what's inside of the parentheses, or is J I H?
Include this. Include this.
Okay.
Oh, sorry. Yeah, you're right. That is my mistake. Here. That's minus.
Okay. That makes sense. Yeah.
Yeah, that is comfortable. Yeah. Okay, and another operator. This is a density, right? So that is values, and we can also introduce this probability operator. We call it probability density operator. is no hat we introduce as a function time, and that is they just cat multiply bra. And we know that is operator, right? If bra multiply cat is inner product different numbers. But if a cat multiply bra, it is operator. So we introduce this operator definition. We say this is a probability operator. And you can see here, because we know, I just use the time evolution of states is the time evolution operator. Right? And if we take the bra time evolution, it's just take bra, so that is just take this conjugate, and U delta, it is a unitary operator. So you can see here the law, the density, probability density operator at any time is equal to, I just substitute this one into here, right? So that is U hat multiply psi of T naught, hat that, and then the bra of T naught, and then apply by the U dagger. So this one is, again, the probability density operator at T naught, right? You see this product. So that is the relation between a time T and the T naught. It is simply just make this time evolution operator U hat. And this one in chapter 2, we also studied this is the time, right? For any the transformation, always follow that the operator has this relation, right? Any operator after transformation, it just from the before transformation and after transformation, they follow this relation. Okay, so this topic, number 6, we discussed how about this time evolution of the probability density. Now, number 7, how about this expectation value? We know expectation value is this the sandwich of the operator in the states. But now, if the states also depend on time, so how about the evolution expectation value evolve or change with time, right? So that is 7. Time evolution of expectation value. This is regard as a measurement, right? So when we measure some observables, which the state change with time, so we are going to see how the expectation value change with time. So now let's assume that we already normalize. If this state, let's first normalize things, that makes the things simple, right? Is normalized. And that means the inner product or self is equal to what, right? Then the expectation value of operator A, for example, is just the sandwich, right? Just this. So the denominator, since the denominator is a number, right? Denominator, this one is not equal to 1, you just first normalize or you just multiply some constant, so that will not affect the result. So in this case, now we are going to look, how about this, right? Total time derivative of expectation value. We are going to look at this one. How the expectation value changes function time. This is what we are going to do. Now, by this relation, since the states and operator all are assume the function depend on the time, right? Function time. So let's keep continuous. So now here, there's a Sully part, right? So we first do the partial with bra. This bra is the function time. And keep operator and the head. Right, that's the first term. second one, we keep the bra and cat, but do the partial duty with respect to operator. Then third one is the cat, right? So we keep bra and operator. Then do this partial cat. Partial cat. Right. Again, since we are going to apply this the Schrödinger equation, right? This part and this part we can apply Schrödinger equation. So we can replace this by whatever the change of time, state with time, the following Schrödinger equation. So we will have the first one. I just since we already did, so then just give you the result. Hamiltonian, yeah, right? This bra. We just take a Schrödinger equation with change the conjugated with that term, right? So that is this one, and I keep here, keep on A. And this one I still keep. Second term still keep here. Change that one, since we do not know how the operator depends on time. That depends on different operators. Third one, this is cat, right? Cat, you see, move this one, we go to the right side from the negative side, right? So negative side I H bar, and A first, Hamiltonian second, right? Okay. So now then we here equal. If I take, you see, if I take IH bar outside, so this is a H Hamiltonian A minus A Hamiltonian, but I change the position. I take this as a first, A Hamiltonian minus this, so I have take minus IH bar outside. Then I multiply I both sides, top and down. So then I have minus 1 minus 10 plus, so the I is equal to denominator, right? 1 over I. Can you sense? Okay. So now this one is nothing but the commutator between between operator A and Hamiltonian. So this first term and third term I combine together, and then leave the second term. Okay, if in simple, just like this, 1 over H bar, and this is the expectation value of this commutator between H and A plus the expectation value of partial operator A this time. So now this is the final relation over how to determine this time evolution of expectation value. What we need to know is first look this whether the operator depend on time explicitly or not. Second, they commute each other, right? So we can discuss in case discussion. First, if the operator does not depend on time explicitly, so the total time evolution of expectation value of this operator for given states is only controlled by its commutator. Expectation value of its commutator. And that is most cases it happens, right? Most cases it is like this. Now the second one, furthermore, right? If does not depend on time explicitly the operator and they commute each other, commute with Hamiltonian. Then the total time derivative of expectation value is constant. It's 0, right? So that means the expectation value does not depend on time. It is constant. So we have a d expectation value equal to 0. So that means this is constant of motion. And when the motion is this operator, right? So what kind of operator? Maybe position, maybe momentum, maybe angular momentum, maybe sum up. So that means we are going to look at the system. The system has its own Hamiltonian. Then we are all interested or try to measure the sum of the interesting physical quantity. So what we are going to see, let's look this, the associated operator of, corresponds to this observables. Whether it does not depend on time or not. Then next, the operator commute with Hamiltonian or not. If both satisfied, then we immediately know, okay, these observable variables will not have. It's a constant motion. That is very important. Let's do one example and it's really a lot of example you can double check. So let's just do one example. We just introduced this operator, right? Probability density operator. Let's look this one. The expectation value of this probability density operator, or if we want to look this expectation value of the probability density, does it depend on time or not? So now let's look this one. Partial. Since we are going to see the first condition, right? Does this operator depend on time not or explicit or not? So now let's look at this one. And we already derived, again. That is, I did it, okay, so now let's do that. First partial cat is time and keep raw. And plus keep the cat and partial raw. Partial keep, right? Again, we are going to apply this Schrödinger equation. So I just do it direct result, write the result since you're already familiar with this. I, or 1 over H bar, Hamiltonian, because it's cat, right? Is cat, raw. And this one is negative, 1 over H bar. Then the cat and raw. H hat. So you can see here that is equal to if I take this minus 1 over I H bar. This is the it is probability density operator, right? This one also probability density operator. So this is nothing but this commutator between these two. So if I make this is I change the order, right? So this one I take this minus outside. So this one is first and this second. So that is the commutator between this. Okay. So now let's look at this total time derivative of this expectation value of probability density according to the formula here. And this one is 1 over I H bar, expectation value of the commutator between the probability density and plus partial rho expectation value of this, right? Then this one, you see this one is nothing. It's just negative of this the first term, so cancel each other. This is a minus 1 over I H bar. Right, so that's equal to 0. They cancel each other. Then that is this excitation value of probability density of it is a constant. This is one example, and if you later I'm going to assign homework, you may have some other operator, and I ask you to double check. You can check that, see whether it is constant or not, right? Okay. Now we discuss the last topic, the seventh is symmetry, invariance, and conservation law. So we're going to discuss the relation between symmetry, invariance, and conservation. They always have this relation, conservation laws. Has relation with symmetry, associated with symmetry. If the system has certain symmetry, means that it will be invariant under such performance or transformation or translation, then it implies there must be associated physical quantities to be conserved. Chapter 2, we already discussed in general, so now let's discuss little bit details like time translation and space translation. So we will see what kind of conservation give us, right? But first, let's consider the translation, right? Symmetry is kind of a translation or transformation related to the whether it's invariant or not, right? So now we are going to consider two cases. One is time, we are interested in translation. And second one is spatial translation. See what kind of physical quantity are associated with those, which are conserved. So now, when we say the translation means unitary transformation, which we discussed in chapter 2, right? Chapter 2. So I just try to remind you for infinitesimal transformation, infinitesimal unitary transformation, we use U, right? Remember U hat, and we have this epsilon, which is infinitesimal parameter associated with such a transformation, right? We use this. And G is generator, right? Operator, generator operator. That is infinitesimal parameter. Remember, we introduced this in chapter 2. And for infinitesimal unitary transformation, the formula is like just about this unitary operator, does nothing change, plus very small infinitesimal change. That is I epsilon G. Remember this formula? That is in general, so we didn't discuss what is epsilon, what is G, the general operator. But the rho, as we say, the general operator, generator, this operator's generator means that generates such kind of performance or such kind of transformation, and associated with the transformation, the parameter is epsilon. So now we are going to discuss what's epsilon and the generator operator, they like pair, like relation between each other, right? So now let's first discuss time. Okay. So now, how about this one? So now we're going to see for time translation, which generator is. So time means epsilon is equal to delta t, right? We have changed time. Then G. What is G? We are going to use our knowledge here. This one's dimensionless.
exponential.
No, this is just unit operator. This is if this unity, this will have same dimension, right?
Mm-hmm.
This is dimensionless. So this product will be dimensionless. Then, so because this epsilon, okay, because delta t g will give us dimensionless. Okay, now let's see. This is time, right? So, g, if let me see, I'm giving you this. So, you see here, the dimension h is a joule, right? I use a square, that means dimension. And h, we know is joule second, right? Okay, so now you see this is a time, a second. And then if a second multiply this one is a joule divided by joule second, so joule cancelled, 1 over second, right? So yes, they make a dimensionless, right? That is how to analyze the generator. Associated with the time, infinitesimal change of time, or infinitesimal translation or transformation of time, associated with generator must be Hamiltonian. Okay, so you see the Hamiltonian. Remember the Schrödinger equation? The Hamiltonian control the change of state in terms of time. So now it's also consistent. So with this, okay, now this operator in the, for time, I'm going to replace epsilon by delta t, and here is Hamiltonian. That is where I come from. And next pair, I want you also do the analysis similar, right? So here that is unity operator plus by epsilon, and epsilon is delta t, and g is Hamiltonian over h bar. Okay, so that is the operator. Now we are going to see what will happen if this transformation, the infinitesimal unitary transformation applied to the states. What will happen? And we say that we transform states from t to another time, right? So now let's see what happens. Okay. Okay, so now let me just keep here. This will not change, right? The first term will not change the states. Second term, I delta t over h bar. Then Hamiltonian apply this. Hamiltonian apply states equal to what? Schrödinger equation, right? So that's be I h bar partial t, right? Okay, so this h bar cancel, we have a minus here. Then this is a 1, so that we have states. Initial states a t and minus delta t partial t, right? And this is like a Taylor expansion at the when we have an infinitesimal quantity or parameter, so that is t minus t delta t, right? From here to here, you agree, right? This is like Taylor expansion. You see that is means it will not change the shape. So does not change the shape of the states or eigenstates or wave function or quantum states, right? What change if it's sinusoidal, still sinusoidal, but only the change time from t to t minus delta t. That's all. So that is what happened. If we use the Hamiltonian as a generator, then that associated with this unitary transformation is nothing but the change time, and this make the states from t to t minus delta t. That is the first. Now let's consider the second. About second, spatial translation. So time translation is one dimension. Spatial translation either like linear momentum, we have px, py, pz, or angular momentum, lx, ly, lz. Let's select only one. Second is a spatial translation. Just do one example, and the others you can follow. Example is okay. Example is epsilon equal to just epsilon equal to displacement along x-axis. Suppose. So if we are interested in the displacement, this unitary transformation just slightly translate the system along x with infinitesimal displacement epsilon. And now we are going to see which generator is associated with this one. Again, we are going to analyze it using the dimensionless, right? So here, this one should be meter, right? So, okay, that means this meter, I use L, right? Okay, let me give you this, and we are going to analyze if it is the linear momentum as well with h. So that this one is kilogram mass, right? And this meter and S inverse, right? And then this joule. Joule is kilo meter square, right? S minus 2, and we have also S. So you see this one cancel, right? There's a minus 2, and this one, so that the kilo, so that is 1 over. Yeah. So this dimension is 1 over meter, and multiply meter, so that is dimensionless. So the generator should be associated with the translation displacement along the x speed, the generator speed, linear momentum along the x direction. So we introduce this unitary transformation u epsilon, which is a px. That speed follow this, right? I plus I epsilon px over h bar. You see the h bar is always important in quantum mechanics. With that factor, a balance law, right? So that is very important. Okay, so now with this one, now we are going to introduce, interesting is this. This is how this unitary transformation acting on states, right? We are going to do the same thing. So now this is a translation in the spatial so that applied to states. Actually, in this case, time does not interesting since we just consider space, right? So you can keep here, it go over now, okay? So that is this unity operator, I epsilon, px over h bar. But now, next one. So now let me write down next step. This first term doesn't change the states. Still keep here because it's not a unity operator. Second one, we have epsilon, I epsilon over h bar. Px. Px applied states. This is in the position, okay. Position minus I h bar partial x. I think that I write down too general, so that make let's consider. Let me replace this one by x. Sorry. Then you do not compute. Let's consider in the position representation. Position representation. then this one is this one also just one dimension since we just move along x, so make this a simple sine x. Yeah. Right. This we already checked this kind of chapter 2. The linear momentum in the position representation is this one, right? And then you can see this h bar cancel, I multiplied minus I is 1. Then that is initial states still keep, and plus epsilon partial sine x, partial x, right? Again, this is a kind of Taylor expansion up to the first order since this is epsilon is the infinitesimal parameters. So that is nothing but do not change the shape of the function, keep the nth function behavior like himself, only change the position from x to x plus epsilon. That is what happens if we have a linear momentum as a generator. What happens? This generator will introduce or generate a translation, which is special translation, which is a displacement, simply just a displacement of this states, right? And since this is also interesting that we consider states, how about this operator? We can also for operator. Then also in chapter 2 we have this unitary transformation A prime is always equal to U epsilon G A U dagger. Right, that is any operator, and the unitary transformation follow this from the before transformation A, after transformation. Right. So now let's look at this position operator, x prime. So after the transformation, how about the operator? This is a state. Right. The operator follow this, right? Then we substitute this formula here, so you will see we have, okay, so I think I have already derived, no space there. This one we already derived in chapter 2 is just keep it later. It's a finite layer. So here, I plus epsilon. Because it's dagger, right? P dagger is because it's a Hermitian operator. So we have first, this one is we have x first, right? This time, and then this one multiply this one to here. That is minus epsilon x p x and phi, right? This one multiply this one, I plus this one. So now the next one is this one multiplied by this, so we have a plus I epsilon p x plus x, and the last one is this one multiplied by this one, so we have is plus epsilon square and plus square, and the p x x p x, right? Since epsilon is very small, so we can ignore this one, or close to 0, just close to 0, right? So approximately is x. Then they have, this is a commutator, right? Commutator between p and I take this one plus I epsilon, or h bar p x is x. The commutator between the position operator and the linear momentum operator. So what is this one? How much? Commutator between position and linear momentum is minus IH bar, right? So that is minus IH bar. Then you can minus, so here we have H bar cancelled, and I became plus, right? So that is equal to x plus h. And yes. that means the operator itself also under this displacement translation, that is the shift. The position operator also simply shift. That is give you how we just discussed transformation, have not discussed symmetry, right? So we are going to keep here. Now this is finite. I gave an example. Now let's go to infinite. Sorry, this is infinitesimal. Now we go to finite. Finite. Same thing in the chapter 2. Put the formula here. Now instead of so here finite A. Let me see, use A or okay, let's use A. So A is the generator, right? So that is exponential I A or H bar, right? Sorry, no H bar. H bar is associated with G. This is an equation in chapter 2, equation 2. Okay, again, for time, so now let's still consider the time translation. How about the finite? It should be the same. So we already discussed that correspond to, if A is time, so now A go to, I can say tau, then the G should be Hamiltonian, right? Hamiltonian or this analysis do the same. Now we are going to apply, so here, now let's see this U tau H apply the states. See what happens. Okay, that is equal to exponential I tau H capital H bar. For finite, we just use Taylor expansion, right? And from 0 to the infinite, 1 over n factorial, and then this one I tau H hat or H bar to the nth power. Now how to do this? So now let's just analyze first the low level and low level order of this H Hamiltonian. Apply this, and then we can induce the high order, and then we can have the results. So because okay, to save time, right? I do not write down the details here. This is partial t, right? So the equation, always. Then how about h squared? Because we have a power n from 0, 1, 2 to the highest. So that is we first do first time. That is h hat I h bar partial psi partial t. And then do again, so then h bar, I h bar is the square, right? And then twice, right? So you do the same thing for the higher order. Therefore here, I'm going to give you the result of u with a finite time. Apply the sine is factorial. Here, I have I tau h bar to the nth power, right? This is a constant. And take h, and for each h n, apply this one to give us I h bar to the nth power. Let's be follow this, right? So you see that this one cancel the I, so then you can see here n from 0 to n 1 over n factorial. That is I is minus 1, right? Minus tau, h bar cancel. So n's power partial n partial t, and this is nothing but this Taylor expansion of, if you extend the eigenstate of the cat, the function Taylor expansion in terms of a t and tau. So that is this one, right? And this one the same as we discussed infinitesimal time translation. That time is delta t here, just tau, the finite time. But we have a similar result, and that makes sense. Similarly, I will also do the same thing. So to save time, I just give you the result and we'll jump the intermediate step. So now this is a time, right? So now let's play space translation. Let's again, now we consider in general is the A will go to is a displacement. 3 dimension, so that is vector. Then we know the G generator we already analyzed that to correspond to the linear momentum, right? And you can again we analyze the dimensions before this. So the finite unitary transformation operates on U. Now I'm going to see the A here vector. Since this parameter is vector now, and this generator is linear momentum. That equal to exponential IA inner product is a P over H bar. Right, so then now let's look how about this state or the cat or the vector under. Now since we do not consider time, just let's look this one. We will not, if it's a time, the dependent time is fine, but it only transfer the spatial translation, right? So we do the same thing here. Then do the Taylor expansion. N factorial y a dot p over h bar n's power. This. And here, this operator, okay, in this case, still we use position representation. Otherwise, the operator is not easy to represent. In position representation, we will not lose representation. We will not lose the general result, right? Position. The P operator is minus I h bar. Gradient, right? Gradient means 3 per partial x, partial y, partial z. So that is this. Then you just substitute into this. So you put here is this is a vector, is number or values, right? So it doesn't matter whatever you have n times, you can take always in front of the operator. So I will just give you the result. Okay, let me just use position. N from 0 to infinite. Manual factorial. And here, now I a dot over h bar. And here, this is a minus I h bar. Reading n's power. Okay, then you can see the h bar cancel, I minus I equal to 1, so that this is inner product, that is two vectors, right? So finally, this is nothing but similar idea. So I just skip the intermediate step. You just follow this and you do this, okay? And similarly, the position operator is in 3 dimensions. That is again we have exponential I A dot P over H bar position operator. And dagger is minus, right? So same thing that if you use a Taylor expansion, oh okay, here I can use this now. So this one, how much equals this? So in the chapter 2, we already discussed any operator for finite unitary transformation. Here, that's equal to the first order, or this order is operator itself, and I, A, O alpha, and the commutator between the generator and operator. Then the second order is I, A, square over 2 factorial. Remember this? And go to height. That is in general, this is equation 260. So we're going to use this. Then now let me here. So R1 is equal to R here plus I. A is vector, right? So the inner product is the generator's P, right? Linear momentum with R and plus higher order. So now the key is this one, right? Okay, we just ignore the high order, so that approximately is R plus. Actually, you don't. Not this exact. Let me write down. So this one, let me plus I A dot. What is this one? Oh, H bar here. PR is constant minus I H bar, right? Yes, minus I H bar. And how about the highest? If this one is constant, any operator will come in with constant, right? So all the high order is 0. The high order, because according to this first order, this commutator is between P and R, that is constant. Then the next one is a P, so constant is a P still commute, that is 0. That makes sense? Okay, so now you see this one, so that is R plus A. And the same as this infinitesimal transformation, right? That is same thing that if in finite we can prove that it is. Okay, I think the time, but I think we can almost finish this symmetry now. We discuss translation, what will happen. So now we are going to discuss if the immerse system will immerse under any time translation or spatial translation, then what kind of conservation physical quantity give us. So now let's come to the last one. Okay. So system, to calculate the system, the operator is Hamiltonian, right? So we are going to look the Hamiltonian because the Hamiltonian calculate system, the kinetic potential energy. That one is the Hamiltonian. So we are going to see how about the Hamiltonian change under the translation, either time translation or spatial translation. The system, right? So that is characterized system. So now, according to the formula here, this one. So under the U value, we'll have this UA, G, H. We are going to see that is, this one is translation or transformation, right? So we are going to do the sum of transformation on the system. Then we are going to see what happened to Hamiltonian. If Hamiltonian invariance will not change, and this transformation to the system, the invariance has a symmetry, right? So, okay. So now let's see here. This one is, according to that, is Hamiltonian plus first order is the commutator between this generator and Hamiltonian. And second one, second order, generator is Hamiltonian and height. Okay, that is in general in the system under the infinitesimal, under this given certain translation or transformation, the system, whether it will invariance or change or not, we are going to look this one. Look whether H prime equal to H, right? So now we are going to discuss. If H prime equal to H, what does it mean? Then the system is in, or system means Hamiltonian, right? Is invariance under the transformation of what generator, right? That is the idea. So because the generator will generate or create a certain type of transformation, like Hamiltonian transform time or the linear momentum the displacement, or maybe later angular momentum gave a rotation. So those generator will have, associated with generator gave a different type of transformation. Now we are going to look, how about the Hamiltonian? If the Hamiltonian does not change under this, then the system is invariant. So that means the system has the symmetry. This is the idea. Under the operation of G, right? Or G associated with G. Okay, now G generated is so that is the idea. Okay, now let's see in which case the system is invariant. Okay, so now that is it, right? Then if, so that's the case if the Hamiltonian commute with the generator, then what happens? This is 0. All higher is 0, right? Then we immediately have this. So that means what we need to see is if the Hamiltonian commute with the generator, we immediately know that symmetry or the system has a symmetry under the operation of this unitary transformation, which is generator is this G. Okay, so that is first, if this, and then if this immediately this, and we have a second one, immediately got another conclusion, because we know this total expectation value, time evolution expectation value, right? The first topic today, the second topic today we discuss. Let's look at this one. That's equal to 1 over, we already derived 1 over H bar, and the expectation value of commutator between the generator and Hamiltonian plus this partial derivative, this one, right? So that means it is equal to, if the generator commute with Hamiltonian, first we know the system has a symmetry under such transformation, which is generated by this generator G. Second, the time evolution of expectation value, this is we know that is also physical quantity associated with this operator. That only depends on the partial derivative of this generator, but in most cases, then we are going to discuss. Then further, right, if the generator does not depend on time explicitly, that is also happen in most cases, then we immediately get this conclusion. The expectation value, time derivative of the expectation value of the generator is equal to 0, so generator expectation value is constant, and this means it's a conserved. So you see here, the G is very important here, right? That is generator. Okay, I think we almost done here. So you can discuss like the G for time evolution or time translation. G is Hamiltonian. Yes, Hamiltonian conserved. That is total energy. If we have this spatial translation, then this if this displacement, linear momentum is conserved. If you have this G is a rotation, then if that rotation commute with the angular momentum commute with Hamiltonian, and angular momentum does not depend on time explicitly, that is conserved. Okay, so I think that is almost the remaining part. I will not discuss about chapter 2, chapter 3. That is some of quantum mechanics related to classical mechanics. And that part, I think you can read yourself. We will go to chapter 4 to apply those postulates. Okay.
Since we're not covering it in class, are those areas going to be in any exam? You just said there were some areas that we can watch up, so we can read over ourselves. Is that a?
No, if you're not covering it, then yes. That's just like reading. Yes, you're not.
Are the labs due like by the end of Monday?
Or, like, we know, like, when does the student have it in? Is that how he does it? I don't remember.
I don't remember. I only know that for have us have back by.
Do you have any makeup like
Yeah, I think that's what it is.
No.
I think it's due by the end of Monday. They
like
would like us to have it
to
graded
set
by
it
the
up
end.
like do you have the tell me
You already submitted your
if anything